The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Okay, so let's pick up where we were on Friday. We had discovered the nucleus, and now we were faced with the problem, as all the scientific community was at 1911, in trying to understand the structure of the atom. Where was the nucleus in the atom? Where was the electron? How were they bound? How did they hang together? And we talked about the fact that the electron in the nucleus, the force of interaction is the Coulomb force. And we started talking about how, at that time, the only equation of motion that was going to allow us to figure out how the electron and nucleus moved under influence of this Coulomb force was Newton's equations of motion, in particular the second law, F equal ma. And so in order to apply that equation of motion, we needed a model for the atom. And what was the simplest and most obvious thing to do was to suggest a planetary model. After all, that's how the astronomical bodies moved around the sun. And so the model that's set up is one where this electron has a uniform circular motion around the nucleus with a well-defined radius, which we call r star. We said that given this, the acceleration was a constant. It was given by v squared over r, the linear velocity over r. We plugged that in to F is equal to ma, put in the Coulomb force. All right. And from that, we were able to calculate the kinetic energy of that electron going around the nucleus. Well, the reason I want to calculate the kinetic energy from this model is because I want to ultimately here calculate the total energy. And why I want to calculate the total energy is going to be obvious in just a few minutes. All right? My goal is to get the total energy. So total energy here, and actually I'm using my notes from Friday because I didn't finish them. So you may need to get them out. And this will probably often be the case, is that I won't quite finish the notes from the other lecture. So I'll start out the next lecture where I left off. Okay? So you should bring your previous day notes to class if, in fact, you use them during class. All right. So I want the kinetic energy plus the potential energy, because I want both of them to add them up to get the total energy. So I know the kinetic energy. Now, we need the potential energy. So what is the potential energy? Well, the potential energy is the integral of the operating force over the appropriate limits. So in this case, if our force of interaction is the Coulomb force that I'll just represent of F of r, I'm going to integrate this from r star out. Okay, and this is going to be minus the integral of the force. Now, some of you may have seen this before. This is a general case. The potential energy of anything is minus the integral of the operating force over the appropriate coordinates. If you've seen it before, that's fine. You're happy. If you haven't seen this before, you're panicked. Okay? Don't panic. I don't hold you responsible for this. You will see it in 801 later on this semester. All right? So when you see it later on, you can come back here and say, okay, now I know what's going on. All right? But I just need it right now to make a point about the total energy of the system. All right? And that's what's going to lead me to the conundrum. Okay? Okay, so I need the potential energy. It's the integral of the force. So let me plug in here my force that's operating, E squared, 4 pi epsilon naught, R squared. I do that integral and put in the appropriate limits. It's minus E squared over 4 pi epsilon naught R star. Okay, so now I got kinetic energy plus potential energy. Let me add them up. So the kinetic is 1/2 E squared, 4 pi epsilon naught R star. Potential minus E squared over 4 pi epsilon naught R star. And the result is minus 1/2 E squared, 4 pi epsilon naught R star. Okay, that's the total energy here of this particular system. Well, why I wanted this total energy is to show you that this total energy is negative, right? What that negative means to us is that the system is bound. The electron and the nucleus are stuck together. And I can show you that maybe a little more clearly if I draw an energy level diagram. So let me plot here the total energy. And I'm plotting it as a function of R, the distance between the electron and the nucleus. Well, what you can see is that for very large R, the energy here, the energy is going to be 0. Way out here for very large R, where we have the electron and the nucleus separated infinitely apart, the energy is 0. And of course, as you bring them closer together, the energy goes down. And when you are exactly, and we calculated this, when you're exactly at R star here, well then the total energy is minus 1/2 E squared over 4 pi epsilon naught times R star. All right? So if you brought this in, the electron and the nucleus into this value here of R star, the energy would change like that. All right? But the big point is this energy is negative, or it's lower than the electron and the nucleus separated. So that means that the electron and nucleus are stuck together. You're going to have to put this much energy into the system in order to pull them apart. That's the big point here, is that this model so far looks like everything is hunky-dory. Everything's working. The electron's stuck to the nucleus. It's not going anywhere. Looks terrific. Okay? But here comes the conundrum. The conundrum is that classical electromagnetism, which was pretty well understood by this time, 1911, 1912, Maxwell's equations, that was down pat. But what classical electromagnetism says is that when you have a charge, and this electron is a charge, when you have a charge that is accelerating, that charge has to be emitting radiation. It has to be giving off energy. All right? After all, that's actually how an antenna works. You know, in an antenna, what you're doing is you're taking charge and sloshing it. You're accelerating it. When it accelerates, it emits radiation. That's how you broadcast. All right? That's true. That was known in 1911. Okay? Synchrotron radiation works the same way. You have a synchrotron. The way you get synchrotron radiation is essentially by accelerating charge. All right? So that's a given. And that's actually, again, something that you will talk about in much more detail in 802. But the point here is, if this charge is being accelerated, and it is, then it must be giving off radiation. It must be giving off energy. Well, if it's giving off energy, we look at our energy expression here. Well, that must mean that the energy of the system is going down because it's losing the energy. It's giving it off to radiation. If E is going down, it's getting more negative here. The only way for E to get more negative is for this R star right here to be changing, is for R star to be getting smaller and smaller and smaller. Okay? Well, we could set up another set of equations using what we know from classical electromagnetism and what we've already done here. And what we would find is that this value here of R star, this value of R star would go to 0 in t equal 10 to the minus 10 seconds if R was originally on the order of an angstrom to begin with. Okay? So here's the problem. Classical equations of motion coupled with classical electromagnetism, they are making a prediction that my atom isn't going to live more than 10 to the minus 10 seconds. Because in 10 to the minus 10 seconds, that electron is on top of the nucleus. We no longer have an atom which was already known to have a volume associated with a diameter that's about an angstrom. Right? The classical way of thinking is making a prediction that isn't consistent with the observations at that time and now. Right? It's predicting that the atom essentially kind of annihilates, that it collapses in 10 to the minus 10 seconds. And that's the problem that the scientific community had in 1911. That's the problem we've got right now, right? And they had it for, 10, 12 years. And now you can say, so what's wrong here? Well, it is possible, and they were thinking about this too, it is possible that, well, maybe, hey, this force is wrong, this Coulomb force. That's a possibility. Or, of course, maybe it's the equations of motion that are wrong. That's possible. Or maybe it's classical electromagnetism that's wrong. Well, of course, what it's going to turn out to be is the equations of motion, F equal ma. Bottom line is that you cannot use classical mechanics to explain the motion of this microscopic particle, the atom, in the constrained environment of an atom. That's the bottom line. We need different mechanics. We can't use classical mechanics to describe how that electron hangs on that nucleus, how they are bound. And so that was the problem, right? This signaled something was really amiss in the scientific community in the world at that time. All right. So that's our problem now, too. So what's the next step? Well, historically, the clues about why the electron didn't actually collapse into the nucleus like classical physics predicted, the clues came from a completely different area of discussion. It came from the discussion of the wave-particle duality of light and matter. It was long believed that matter, with its particle-like behavior, that was distinct from light, which was this transmission of energy through space. But in the late 1800s and early 1900s, there were a few experiments that appeared on the horizon that began to suggest that maybe this boundary between matter with its particle-like behavior and radiation with its wave-like behavior, that, well, maybe that boundary wasn't as rigid as thought. And in fact, what we're going to see is that radiation has both wave-like properties and particle-like properties, and it depends on the particular experiment that you do, which one of those behaviors you see. And consequently, then matter. Matter behaves both as a particle and a wave, and again, it depends on exactly what experiment you do, which one of those properties you observe, right? So what we're going to do right now is that we're going to put aside the discussion of the structure of the atom. We're going to put it aside until next Monday. And we've got to do that because we need some more information in order to take a big leap to get us out of this constraint of classical mechanics. And those clues, as I said, came from this discussion of the wave-particle duality of light and matter. And that's what we're going to be talking about for the next 3 lectures. And then we're going to come back and we're going to tie in those results to the structure of the atom. And of course, where that's going to lead us is a new mechanics, a new equation of motion called quantum mechanics. Okay? So that's where we're going. All right, so let's start off. We're going to start off by talking about radiation, or light, and we're going to talk about its wave-like properties. Then Wednesday, we're going to talk about the particle-like properties of light. And Friday, we're going to talk about the wave-like properties of matter. All right? So that's where we're going. Okay. So let's talk about waves here. All right, so you all know that waves are some periodic variation of a quantity. So a water wave, for example, is a periodic variation of the level of water. At some points in space, the water level is high. At other points, the water level is low. Sound wave. Well, a sound wave is the periodic variation of the density of air. At some points in space, the air is very dense. At other points in space, the air is not dense. All right, well, light or radiation, it is a periodic variation of an electric field, as I depict here on this slide, electric field versus position. There's a periodic variation of the electric field. But now, exactly, what is an electric field? Some of you know this, some of you don't. But an electric field is literally the space through which the Coulomb force operates. So for example, if we have a negatively charged plate and a positively charged plate here, the space through which the Coulomb force is operating here, and the Coulomb force is operating because we've got 2 plates here that are oppositely charged. So the electric field here is operating in this, the electric field is the space through which the Coulomb force operates. If we put a positive charge in that space, well, you know what's going to happen. In this coordinate system, the positive charge is going to float up because the negatively charged plate is up above. If we reversed the potential difference, and we put a positively charged particle in this electric field, in this space, it's going to move down because now the negatively charged plate is lower. So this electric field here has not only magnitude. You can imagine here the magnitude is given by the difference in the potentials of these plates. The larger the difference, the larger the magnitude. But it also has direction. In one case, it's pointed this way, right? In the other case, it's pointed that way. And that's reflected here on this plot of the electric field here. What you see is that right here, the magnitude of the electric field is small. As you move along in X, that magnitude increases, goes to a maximum, then turns around. And at some point, it literally is 0. And then the electric field changes direction, and its magnitude increases in the opposite direction, right? Increases, gets to a point, then turns around, and becomes 0 again. So if you had a charge in a radiation field and you put it right here, well, it would be pulled in one direction, but if you put it over here, it would be pulled in the other direction. All right, so we have a magnitude and we have a direction. Now, not only is light a periodic variation of the electric field in space, but it is also a periodic variation of the electric field in time. That is, this is a picture of that field at one instant in time. We'll call it t equals 0. However, that electric field moves. It propagates. And the distance, or the time it takes, for the electric field here to move over one wavelength, so I've shown this as a star. The time it takes for this maximum to go from here to here, one wavelength, is defined as 1 period. And a period is given by 1 over nu, where nu is the frequency of the radiation. It's the number of cycles per second. So in other words, if you were sitting here at x is equal to 0, right? You were tied at x equals 0, and you were just watching this electric field come by, you would see a maximum in that electric field, one maximum every second, if the frequency is 1 hertz, right? Or in other words, the frequency is the number of maxima you would see pass by you per second, right? Okay, well, we have a unit to characterize frequency. I called it cycles per second. It is cycles per second, but the formal unit is hertz. Hertz is inverse seconds. So we leave out the number of cycles. The number of cycles is implied in the unit of hertz. So to make this, to give another example here, suppose we had some radiation, and the frequency of that radiation was 1 hertz. And suppose we had an electron. Electron is charged, and we put that electron here at x equals 0. All right? Now, and we tie it at x equals 0. Well, what's going to happen to this electron? Well, what's going to happen is that this electron is going to be pulled down, and then it's going to be pushed back up once every second, because the frequency here is 1 hertz, right? It's charged, and we're tying it at x equals 0. It's going to go like this. It's going to oscillate once every second if this frequency is 1 hertz. So here it goes. Electron is pulled down and then pushed back up once every second. All right? Okay, now, we, of course, can write an equation to describe this oscillation of the electric field in both space and time. X is the position variable, t the time variable. And I've written it down here, and I'll explain this more in just a moment. But what I also want to point out is that an oscillating electric field always, always, always has perpendicular to it an oscillating magnetic field. All right? That's well described by Maxwell's equations. Again, you're going to see that in 802. And the magnetic field here has the same essentially functional form, characteristics as this electric field. And because it does, I'm just going to talk about the electric field. But here is the expression for the magnetic field. I just call it H. But again, it's a function of position and time. And here's an illustration of just the variation of the electric field. So light radiation is actually a variation in space and time of both the electric and a magnetic field. That's why it's electromagnetic radiation. Now, let me show you on the 802 website. Can we get that rolling? Okay. Oh, there it is. Okay. And now we have to start it. All right. So one of these is the electric field. The other one is the magnetic field. This is a simulation that 802 has made for you. You can go and look at it on the 802 website. But you can see it propagating here in time. And you can see its variation in space of this electromagnetic field. Okay. So let's look at this functional form just a little more carefully, just to make sure everybody's on the same page. I think many of you have seen this before. What we're going to do is, because we have two variables, we're going to hold one variable constant and plot it as a function of the other variable, just to explain the parameters that go into this functional form. So at time t equals 0, if in this equation here I stick in t equals 0, I have a form that looks like this. It's just the cosine function in x. And you can see that the amplitude goes from positive a to minus a. All right? And so what you see is that this a in front of the cosine, the physical meaning of it, is just the maximum amplitude. So if you were given a functional form with a number in front of a cosine, well, you could read off the amplitude immediately. Okay. The other parameter that characterizes this wave is the wavelength. It's the distance between two successive maxima or two successive minima. And you can also see here that the field is going to be at its maximum amplitude whenever this x is an integral multiple of the wavelength, lambda, 2 lambda, 3 lambda, or minus lambda, minus 2 lambda, or 0. All right, so if you were given a waveform and there's a number in front of the x, you can almost, by inspection, tell what the wavelength is. That number would be equal to 2 pi over lambda. Okay, and now what we're going to do is we're going to hold x constant, and we're going to set it equal to 0, and then plot this functional form as a function of time. And again, we have the cosine function, oscillates from plus a to minus a. And now the time between two successive maxima or minima is what we spoke earlier of as the period. It's the time for one cycle. Or in other words, it is 1 over the frequency. And you get the maximum then whenever the time is an integral multiple of the period. So whenever time is 1 over nu, 2 over nu, 3 over nu, or minus 1 over nu, minus 2 over nu, or 0. Okay? All right, so these are the characteristics of the functional form: amplitudes, wavelengths, frequencies. Now, I told you that the period was given by 1 over nu. Let's just do a quick proof that the period is actually 1 over nu. All right, it's 1 over frequency. So how we're going to do that? Well, what I said was the definition for a period was the time it takes the wave to move one wavelength. So if this is the wave at t equals 0, this then, coming up here, should be the wave at one period later. And so if we've moved over exactly one cycle, what this means is that at one period later, the functional form ought to look exactly like it did at t equals 0. So if I take my general expression for the waveform and I plug in t equal 1 over nu, I get this. All right? What you can see at first glance is that it doesn't really look like this, or at least not just yet. But we're going to make it look like this, and we're going to do so legally. Okay? So what are we going to do? All right, so this just repeats that equation. Hey, you can already see we've got some cancellation here. These two n's go away. So I just have cosine 2 pi x over lambda minus 2 pi. Now, in order to simplify this, I'm going to need a trigonometric identity, which you may or may not remember. Right? Cosine alpha minus beta is the cosine alpha times cosine beta plus the sine of the alpha sine beta. So I'm going to let 2 pi x be alpha, and beta will be 2 pi. I'm going to plug that in. And here we can see some nice simplification. This cosine 2 pi, of course, is 1. The sine of 2 pi is 0. Hey, this term goes away. And what I got left is a cosine 2 pi x over lambda at t equal 1 over nu. And indeed, that is the same functional form as the field at t equals 0. So that's our proof, right, that the period is equal to 1 over nu. Okay. Now, this wave also propagates in space. It moves. You know, it goes from here to here. All right? And another important characteristic of electromagnetic radiation is the speed with which it propagates. Let's just quickly calculate what that speed is. We have enough information to do that. Speed is always distance traveled divided by time elapsed. And we said that at t equals 0, this is what our waveform looked like. We also said that one period later, this is what our waveform looked like. We know at one period that the waveform moved over one wavelength. So the speed is the distance traveled, which is a wavelength, divided by the time elapsed, which is 1 over nu, the period. And therefore, the speed is lambda times nu. That's the speed with which this wave propagates. And of course, you already know that electromagnetic radiation, all electromagnetic radiation, has a constant speed of about 3 times 10 to the 8th meters per second, or we call it c. Right? And what that is the product of the wavelength times the frequency. The electromagnetic spectrum, of course, is infinitely wide. And here is the electromagnetic spectrum. We won't do this in any kind of detail. But I just want you to note here that on the long wavelength end, we have what we call radio waves. On the short wavelength end, we have our gamma rays and cosmic rays. And in the case of the gamma and the cosmic rays, because the wavelength is small, lambda small, that means those waves have a high frequency. In the case of the radio waves, because those wavelengths are long, that means those waves have a lower frequency because the frequency times the wavelength is a constant. It's this c. It's 3 times 10 to the 8th meters per second. Okay? And of course, right in here, very small region, narrow region of the electromagnetic spectrum are the light waves that are sensitive to our eye. What you do need to know is that the red wavelengths are longer, the blue wavelengths are shorter. Okay? So again, the important thing is lambda times nu is always, for every kind of radiation, equal to a constant. And that constant is a c. Now, the other thing that you just need to know is the relative ordering here in wavelengths. You do need to know that microwaves are longer wavelengths than gamma rays. Okay? All MIT students should know that. All right. Oh, and one other thing I might say, because we're going to talk about this a little later in the course. See these microwaves? Well, molecules will absorb microwaves, take it in. And that kind of radiation is going to set the molecule rotating. Molecules will absorb infrared radiation. And that kind of radiation is going to set the molecules vibrating. Molecules will absorb visible and ultraviolet radiation. And what that's going to do is promote an electron to an excited state. And then sometimes those electrons in the excited state, they want to relax back down to the ground state. And when they do so, they give off radiation. And that's the origin of fluorescence. It's sometimes phosphorescence. Okay. And then sometimes molecules will also fluoresce if they absorb X-rays. But with X-rays, if a molecule absorbs them, it also kicks out an electron, and we'll be looking at that in a few days to identify the energy levels of molecules and atoms and molecules. All right? Okay, so this I think you're familiar with. Now, so far I've just told you what electromagnetic radiation is, how we characterize it, speed, frequency, wavelength, maximum amplitude. But what I haven't shown you yet is any evidence that indeed light has wave-like characteristics. And to do that, we're going to do the experiment that essentially was done to demonstrate the wave-like behavior of light, and that's Young's two-slit experiments. This is the late 1800s. And what was done is to take a source of monochromatic radiation. We're going to use 6,330 angstroms, 633 nanometers. It's a helium neon laser. And it's going to impinge on just a thin metal plate. Doesn't have to be metal, can be anything. But what we did is we poked two holes in it. We made two slits. And naively, you might think that that radiation, if you looked at a screen out here, naively you might think that the screen will light up in spots that are directly opposite those slits because, hey, after all, light travels in straight lines. And so if the slits here are 0.005 meters apart, you might think that the two bright spots on the slit will be about 0.02 inches apart. Well, of course, that isn't the case. And what you really see is you see an array of bright spots. And Christine has up there in the projection booth a helium neon laser that's shining behind two slits. Oh, you got it really beautifully now, Christine. That's great. And what you see is that there's a whole array of spots, right? There aren't just two spots. There is a bunch of spots here, bright spot, dark spot, bright spot, dark spot. You've also got another pattern superimposed on that. It almost looks like, gee, it almost looks like you'd see the single slit diffraction too on top of the double slit. But we won't get into that, all right? But this is not, all right, just two spots. So let's see if we can try to understand how this pattern arises, okay, what this pattern comes from. All right, well, waves have the property of superposition. And superposition means that if I take a wave and I have it in space, but now I take a second wave and I put it in the same place in space, but I make it such that the maxima of both waves are in the identical place in space. What I have is a situation where the two waves add. That property of addition of waves when they're in the same place in space, that property is called superposition, and that's the property of waves. And in this particular case, we're going to have what we call constructive interference. They're going to add up such that the amplitude here of the resulting wave is going to be twice the amplitude of each of the individual waves. This is constructive interference. On the other hand, I can have two waves in the same place in space, but they can be positioned so that the maximum of one wave is at the same point in space as the minimum of the other. And because we have these positive and negative amplitudes, well then these are going to cancel when they add up, and we're going to have the null result. We're going to have no intensity. That's called destructive interference. Okay? All right, well, in order to understand how this property of interference gives rise to these array of bright spots in the two-slit experiment, let me actually use water waves as an example to try to understand why we get this array of spots, or this row of bright spots and dark spots, right? So here is the beach. Here's the water. This is the top view. Here's the water. Here's the sand. Here is where I wanted to be all weekend, right? And the waves are rolling in to the shore. There are the wave fronts. And then suppose I get ambitious and for whatever perverse reason I decide to build a barrier, right, to prevent these waves from coming on the beach, except I poke 2 holes in the barrier, right? 2 little holes. Well, you know what's going to happen is that when the wave approaches that barrier, well, through that little hole, a little bit of the wave is going to sneak through. And because that little hole is really pretty little, what's going to happen is that that wavefront is going to spread out isotropically. And so that wavefront is going to look like a semicircle centered on that little hole. And of course, this wavefront is going to keep propagating. And it propagates out, and then soon enough, a wavelength later, hey, another wave sneaks through, and I got 2 semicircles. That keeps, and the distance between those 2 semicircles is lambda, right? That's the wavelength, because that is that's the wave crest. That's the maximum of the wave. Keep going, that propagates out. Keep going, that propagates out. Well, at the same time that the waves are sneaking out through that little hole, the waves are sneaking out through this little hole, and I will color them green. All right? That wave propagates out, keeps propagating. The other one sneaks through, keeps propagating. And now let me clean up the drawing a little bit. And I'm going to call this slit 1. So the green waves are the waves that have come through slit 1. The blue waves are the ones that have come through slit 2. And the distance between any 2 successive maxima here, or any 2 semicircles, is of course lambda. And lambda is the same for slit 1 and slit 2. Now I want you to look at this spot that I just circled. All right, right here. What do you see? Interference, absolutely. You've got 2 maxima at the same place in space. You're going to have constructive interference right there. What about this spot? Constructive interference. What about this spot? Right. Everywhere along that line, you're going to have constructive interference. All right? Let's look at, whoops, all right. Now, let me just tell you one other thing. So we got every constructive interference all along this line. Now look right at this point here. What you see is you have the superposition of the blue wave that has come from slit 2, and this blue wave has traveled out from slit 2 a distance 4 lambda, right? 1, 2, 3, 4 lambda. That's the radius. It's traveled out a distance 4 lambda. It is constructively interfering with a wave coming from slit 1 that has traveled out a distance 3 lambda, right? 1, 2, 3. The difference in the distance traveled by those 2 waves that are constructively interfering is 1 lambda, right? Let's keep going in order to understand this diagram. Let's look at this spot. Right here, what do you have? Constructive interference. Right here, you got constructive interference. If you kept going, you'd see everywhere along this line, you're going to have constructive interference. Now, let's look at the difference in the distance traveled by the waves that are constructively interfering along that line. Well, you see the green wave here? The wave that's constructively interfering is one that has traveled out a distance 2 lambda. That is, r sub 1 is equal to 2 lambda. It's interfering with this wave front that has traveled out a distance 4 lambda. The difference in the distance traveled by those two waves is 2 lambda. It's 4 lambda minus 2 lambda equal 2 lambda. I think on your notes, it's actually this case that I've written it down. Okay? Here's another point of constructive interference. Here's another point of constructive interference. Everywhere along this line, we have constructive interference. And if you analyze this, the difference in the distance traveled would be 0. Okay? So what you would expect here is, if you were to image this, you'd expect right here very bright spot, very bright spot, very bright spot. And this is going to be symmetric around the center. So there'll be a bright spot out here, bright spot out there. Let's look at this actually in real life, in a water tank. And there we go, up here on the sideboards. Okay. Ooh. All right. Here are the waves coming this way onto some barrier, and here are the holes. Here's one hole. Here's the other hole. And then these bright semicircles are the wave fronts. And what I want you to notice, and you have to kind of look out here, right? You see right here, right there, you see a whole bunch of very bright spots. Well, if this were light and we had a screen, then right here we'd see the screen light up. And then right here, you see kind of nothing. That nothing is destructive interference. That would be a dark spot if, in fact, this were light and we were looking at a screen. And then here's another very bright spot. Here's another very bright spot. Okay? This is on a website from the University of Colorado, which, if you're not familiar with, is actually kind of a very neat website. It has some very elementary topics in it, but it also has some topics that even you would be interested in. Okay? Okay. And that is actually the name of the website. And so what's going on here in the case of the light is just what we've explained. We've got this line of constructive interference that's going to result on the screen as a very bright spot, and then another line with another bright spot, and another line with a very bright spot. And this is symmetric around the 0. So right at this point, we got constructive interference. In between, we got destructive interference, constructive, destructive, constructive. And that's the origin of the many different bright spots. And now, there is a condition that has to obtain in order for there to be constructive, maximum constructive interference, and that is this condition. The difference in the distance traveled of the two waves that are interfering to give us that maximum constructive interference has to be an integral multiple of the wavelength. All right? I'll explain this a little bit more starting on Wednesday. Okay, see you then.